This is our second video on the ideal gases, and this one is on the combined gas law. The ideal gas law is PV equals nRT. If you take a specific set of conditions and label that condition 1, you can now label the ideal gas law P1V1 equals N1RT1. You can rearrange it so that P1V1 divided by N1T1 equals R, and R is a constant. That value is not going to change. That's why it's called a constant. So now if you change the conditions of the gas and are now in condition number 2, you can write that P2V2 equals N2RT2. That can be arranged to P2V2 divided by N2T2 equals R. So P1V1 divided by N1T1 equals R, which is equal to P2V2 divided by N2T2. But if A equals B and B equals C, then you know that A equals C. So you can rewrite this as P1V1 divided by N1T1 equals P2V2 divided by N2T2. This is called the combined gas law. This can be used to solve for a variable if you have two sets of conditions for the same gas. An example, you're at the base camp of Mount Everest. There, the air pressure is 0.525 atmospheres, and the average temperature is minus 4 degrees Celsius. You fill a Mylar balloon to a volume of 370 liters. You release the balloon so it floats to the summit, where the pressure happens to be 0.333 atmospheres, but the temperature is minus 31 degrees Celsius. At the summit, what is the volume of the balloon you released? We're going to do a modified gas system. We know that P1 is 0.525 atmospheres. V1 is 370 liters. We don't know the number of moles. It's some number. Let's call it N1. The temperature in Kelvin is 273 minus 4 degrees Celsius. That's 269 Kelvin. This pressure at the top is 0.333 atmospheres. That's P2. We don't know the second volume. That's what we're looking for. We haven't added or removed any gas, so N sub 2 is equal to the number of moles under the first condition, so N2 equals N1. The temperature in Kelvin is 273 plus the temperature in Celsius. The temperature in Celsius is minus 31, so you get 242 Kelvin. You set up the combined gas law, but N2 equals N1, so it can be rewritten this way. Since you have N1 in the denominator on both sides, that cancels out. So the equation simplifies to P1V1 divided by T1 equals P2V2 divided by T2. Plug in the values, rearrange to solve. Notice the atmospheres cancel out, the Kelvin cancel out. You're left with liters, which is the volume you're looking for, and you get 525 liters. Pretty straightforward. Here's one for you to try. Come up with the answer, check it, and then we'll walk through it. So you've got a rigid 125 liter container. That means the volume of the container can't change, and it has 2.46 moles of a gas, and the pressure is 816 torr. You don't change the temperature, but you add more gas until the pressure becomes 1088 torr. How many moles of gas were added? Go. And if you came up with 3.28 moles, you're incorrect. Why? Let's walk through it. The initial pressure is 816 torr. The initial volume is 125 liters. N is 2.46 moles. T1 is T1. We don't know what the temperature is. The second pressure is 1,088 atmospheres. The second volume is 125 liters. It's a rigid container. The number of moles is unknown because we've added some, and T2 equals T1. So we set this up as a combined gas law equation. We know that V1 and V2 are the same, and T1 and T2 are the same, so they will both cancel out, and you end up with P1 divided by N1 equals P2 divided by N2. Plug in the values, rearrange, solve for N2, and you get 3.28 moles. And now you say, but you said that that was the incorrect answer. It is. Read the bloody question, answer the bloody question. The question wasn't how many moles are in the balloon. The question was, how many moles of gas were added? You ended up with 3.28 moles. You started with 4.26 moles. When you subtract them, it means you added 0.82 moles. That's the correct answer. Read the bloody question, answer the bloody question. So to review, you start with the ideal gas law, PV equals nRT. You need to memorize this. You can do a little mathematical wizardry, and you get the derived combined gas law, which is P1V1 divided by N1T1 equals P2V2 divided by N2T2. This is useful when you're comparing one set of conditions to another. And I'm going to remind you that the gas behavior at the particulate level is explained with KMT. In the next video, I'm going to deconstruct the combined gas laws and merge that with the kinetic and molecular theory to wrap everything up.